No, Fabrizio is speaking now, and I'm in the same room with Matteo, and I will start, and Matteo will continue until the end of the presentation. And we are both with the University of Cagliari in Italy, and I'm also involved in ISGAN, and particularly I'm responsible for Annex 3, that is exactly about cost-benefit analysis and socio-economic impact of smart grids. And this afternoon, with this webinar, we would like to give you some information about what is going on in ISGAN regarding the topic, the important topic of decision-making related to smart grid projects. And this is also a way to make a kind of advertisement. If you are interested to our activities in ISGAN, we are very happy to welcome you on board. But what is ISGAN for someone that maybe this is a brief outline of the presentation. As you can see, the first item in the list is about ISGAN. So just a few words about ISGAN. ISGAN is the strategic platform to support high-level government attention and actions for the accelerated development and deployment of smarter, cleaner electricity grids around the world. It is an initiative of the Clean Energy Ministerial, CEM, and it was organizing as the implementing agreement for a cooperative program of smart grids. And so it's also something that depends on IDEA, the Energy Technology Network in particular. And the CEM is the only multilateral forum dedicated exclusively to the advancement of clean energy technologies and related policies. And ISGAN is the only global government forum on smart grids. And about the activities of ISGAN, as you can see in the slide, we have 8 annexes that each one is responsible to deal with a specific topic. And so we have Annex 1 that is about the global smart grid inventory. We have Annex 2 that is about case studies related to smart grids. Annex 3, that is the annex that I chair, is about cost-benefit analysis and toolkits for dealing with cost-benefit and decision-making. Then we have Annex 4, Insight for Decision Makers, and Smart Grid International Research Facility Network. It's about facility and facilities and laboratories. And then we have Power and Transmission and Distribution Systems, Annex 6, and Smart Grid Transition, Annex 7. And finally, Annex 8, that is the Smart Grid Academy, the ISGAN Smart Grid Academy, that is the organizer of this webinar. And just to give you an idea of how many countries and institutions are now involved in ISGAN. And as you can see, all the world is covered by ISGAN. So now I think that it's time to start with the presentation, and just a few words about the context and the motivations. And well, the smart grid transition is something that is really a reality now, and there are some key drivers. Everyone knows that we have environmental and regulatory pressure for smart grids, and the market liberalization is a reality in many countries, and the security of supply and quality of services are something that we do want to achieve in our systems, and we don't have money for to rebuild everything, and so copper investment postponement and using and exploiting at maximum level existing assets is another key driver for smart grid. And we are depending more and more from renewable energy sources, and we want to do more in Europe and in many countries in the world. There are so many programs for increasing the level of renewables. And another important point is that in order to manage so much not programmable and dispatchable energy sources, we need to add to the system a lot of flexibility, much more than in the past, and we should leave the load following paradigm towards a more modern and more difficult generation following without changing our habits. And so flexibility with storage, with electric vehicles that are another kind of storage, with active demand participation are all things that require smart grids in place. And so the challenge is the complexity is increasing. We need to integrate effectively distributed energy resources, and we need a dynamic optimization of grid operation and resources. And we should incorporate in our systems demand response. And for sure, we want to have self-healing, more reliable and more resilient systems. And we need to increase cybersecurity and interoperability. And that means that smart grid is really a complex topic that requires an holistic approach. And so it's so complex that there is the need of a huge amount of investments, and so this is the most important point for cost-benefit analysis. The question is how to allocate efficiently the budget for innovation and for smart grids particularly. Smart grids, as you can see here, typically can enable a lot of a wide range of services, and those services have high and significant socio-economic impact, and so a wide range of impacts, a lot of indirect and side effects, a lot of intangible impacts, and we have few data because we have just started, and we have a lot of uncertainties. So that means that not only monetary aspects are of interest. And let's think about environment as a clear example of something that is not really only about money. And then we have the difficulties to allocate the impacts and benefits. And quantify with money all impacts is not always simple. Or if we try to do, we have to do so many assumptions that in some way we change the accuracy of typical cost-benefit analysis. And finally, most important, all these decisions are to be made under an increasing level of uncertainties, much more than in the past. And so that's another point to think about. Which is the scope of decision making is something well known. Well, we have to identify the best, or let's say the best option in a limited list of design options. And so we have to assess the different options and the performances. So it's a question of metrics, how to measure the performances. And then we have to find a good compromise, since this decision making is not only about one stakeholder in the context of smart grids. It's different from a company. If you work in a company, you know exactly which are the stakeholders. But if you are talking about smart grids, the stakeholders are many. We have the society, we have a lot of companies, we have people, and we have politicians and governments and many stakeholders, and each of them has different goals, so we have to find reasonable compromises in order to identify which is the best option. And finally, we can conclude that under the umbrella of smart grids, we do need effective tools for complex decision-making problems in order to identify where it is better to allocate resources for development. And one very well-known tool or methodology for analyzing for decision-making is the cost-benefit analysis. Cost-benefit analysis, CBA, is one of the most acknowledged tools for assessing the financial viability of industrial projects. And if we apply cost-benefit analysis, well, with CBA, we seek for an optimal resource allocation. In particularly, we want to find a solution that costs less than the benefits, and we should find, in this way, we seek for the most profitable investment option, and it's very easy to read because it's only, everything is about money. So if the money we spend is less than the money we earn, that alternative, that project is good. And if I want to do a ranking, it's quite easy to do a ranking because the most profitable is in the first position, and then we can prepare a list according to the level of income we can receive. It's very easy to say, not too easy to apply in a smart grid context. And typical parameters that are used are the net present value for the net benefit produced. It's very critical, the internal rate of return, IRR, the discount rate value that makes the NPV equal to 0, and the cost-benefit ratio, that is the ratio of the present value of benefit and cost. All these three indicators are the common output of CBA. So these are in this slide you can see the typical steps of CBA: target and content recognition, the cost and benefit quantification, monetizing and discounting, cost and benefit aggregation, and then finally you get NPV, IRR, and CBR, and finally you can also perform some sensitivity analysis if some of the data in your calculation are uncertain. And CBA has been applied for many years in companies, and recently CBA is used also for allocating public money, and there are many regulatory frameworks in the world that require a positive CBA for approving a project. In Italy, for example, cost-benefit analysis is now applied to investment in the transmission system. The TSO, if the TSO proposes a new investment, the proposal should come with a cost-benefit analysis in order to justify the investment. So it's the same for smart meters, and cost-benefit analysis is really becoming crucial for many investments, particularly in power systems. And well, since CBA has been used for many years and many specific guidelines have been developed and published by government bodies, and you can see that we can immediately see that if we try to apply CBA for very big projects that affect country or large part of the country, CBA has some drawbacks and shortcomings. And the first problem is about the quantification. Quantifying intangible impacts are not clearly quantifiable, and so we can do only some qualitative assessment. Monetizing, this is another point. The monetization of everything related particularly to smart grid is not that easy, and there is the risk of misrepresentations. And discounting of intangible impacts appears unsound because it leads to an increased burden on future generations. It's something that is really happening now because we are destroying our environment and we are leaving the burden on that on the shoulders of next generation. So something that is very difficult to deal with a simple cost-benefit analysis. So cost-benefit analysis is very good for decision-making applied in the private sector. People is involved as a customer. Goods and services are exchanged within a market. Tangible impacts are the majority, and the investor target is simple, just maximize the profits. And if we try to apply CBA, pure CBA, to a public sector, and people are not customers, are citizens and our taxpayers, some goods and services do not have market. Intangible impacts are not negligible, and investor targets is maximize the efficiency and the effectiveness of investment, not the profit. And key issues for applying in the context of smart grids cost-benefit analysis is to obtain an effective classification of impacts, and there is a high risk of double counting. And this is very, very important to think about. And we should obtain a multiple number of feasible future scenarios. And another point is key issues is forecast of prices, particularly of new technologies, is not very easy to perform. And identify and consider the synergy of different smart grid assets is again another issue in the application of cost benefit. And finally, it's very difficult and tough to generalize methods and results on different countries. And another way to deal with decision making is, well, I say another way, in reality there are some complementarities, but anyway, another way to deal with decision making is multicriteria. Multicriteria helps decision makers identify the best option among a given set of different alternatives or design options. And it's a very well-known methodology for complex decision making. Encourages MCA encourages the common decomposition. It's very good to understand to deal with conflicting criteria that are very common in complex smart grid projects. And tangible and intangible impacts can be dealt with simultaneously. And also qualitative indicators can be used with MCA. And we can directly include different point of views, different stakeholders in the evaluation process. And it's very good for the application of probabilistic models. So this is MCA. And MCA is a very well-known methodology, and the main there are many different techniques that have been developed, but we can try to split into two different families. One is the multi-objective design making, MODM, that design a set of optimal solutions by minimizing the objectives. And the other one is multi-attribute decision making that finds the best alternative among an explicitly known set. And the steps for the application of MCA and ADM is again target and context recognition, identify the alternatives under analysis, identify evaluation criteria, scoring of alternatives, weighting of alternatives, score and weight combination, result analysis, and if it is necessary, and sensitivity analysis with reference to the most uncertain and significant elements of the project. And regarding MADM, you can see here a list of different approaches: the full aggregation approach, FAAA, the outranking results, OM, and the goal aspiration approach. And to the right column of this slide, you can see also some algorithms and tools and even software that can be used for for solving decision making with reference to each one of these big families. The key elements of multi-criteria MADM methodologies are the hierarchy for criteria, the performance matrix, and the stakeholders value scale. The output of each of these criteria, performance matrix, and stakeholder value scale are all used by the MCA technique in order to prepare a ranking for a list of limited list, finite list. This is a clear difference between multi-criteria and multi-objective, and this is about the number of alternatives. If you have a limited list of options, then we are in the field of multi-criteria, and multi-criteria analysis is capable at the end to give a classification and ranking of a list of projects. Well, cons of MCA. MCA is not oriented to profit, and so no explicit rule for obtaining benefits that exceed cost. The identified best option, design option, may not pursue with big improvements, and doing nothing principle might result as preferable. Subjectivity is directly introduced by criteria weights and qualitative appraisals of alternatives. And effective strategies for reject personal biases need to be employed. Another point is the multiplicity of MCA and ADM techniques. There are so many that it is not that easy to identify which is the best suited to the application. And many of these techniques are very complex, very good for academic exercises and researches, but not that easy to be used outside the academic community. So some gaps. Within Annex 3, we deeply studied CBA as a starting point for decision making applied to smart grids. And we have prepared some reports, and if you are interested to know more about our activities in ISGAN regarding the point of CBA, you are really invited to surf the internet and look for our documents that we have recently changed the website and the portal, but we are putting there all documents and reports, and so you can find more detailed documents on ISGAN activities. And as you can see, we have identified with the cost benefit some gaps. And cost benefit analysis applied to smart grid started with EPRI. EPRI is a pure application of cost benefit analysis. And from EPRI, there are some interesting activities. As you can see, GRC, the European Joint Research Center, changed a little bit from EPRI, and as you can see in the diagram, it is less quantitative than EPRI, since EPRI is only, again, based about money, and GRC tried to contaminate a little bit CBA with other techniques like MCA. And several methods applied are specific for case studies. Several other methods are general, and GRC and EPRI are examples of that. And there are some methods that consider only quantitative criteria, and there are some others that are tried to move from quantitative to qualitative. And some application of decision-making and cost-benefit analysis, some examples, and which is clear is that we need a large amount of input data for this kind of studies, and the analyst, high analyst know-how is very important, and another gap and weak point is that we have low replicability, and so it's very difficult to replicate one CBA from one study to another one, and difficult to replicate on different contexts on different assets. And also results are difficult to be compared from different frameworks. And finally, in Annex 3, we have identified some gaps for the application of CBA in the smart grid context, and those gaps are also good starting point for future research. And one point is that we have limited feedback from real smart grid projects, and so it's very difficult to get data for studies, and it's very difficult the application in different contexts. So this is one point. Another point is that we do need to include something that is not easy to be quantified, and another point is that we should try to simplify the decision-making process. And so the result and the recommendation is try to improve novel methods based on CBA and multicriteria. And another interesting point, particularly it is being stressed in Sweden, but it's very interesting, is that when we do CBA, maybe we can find that the project is not convenient, but what is really could be really useful is finding the way on how to identify what is the weak point of the project, and how can reuse that study for improving a project that is not really good enough. And another crucial point is that uncertainty and also regulation, how to deal with uncertainties, how to deal with regulation and decision making. And particularly the level of uncertainties is getting so high that the sensitivity analysis is not enough. And so we have to improve our methodologies on that. And I think that this was just to give you a picture of the main differences between CBA and MCA. And now is the time to go in the second part of presentation, and this is about the combined approach of both techniques, and also to see some example of applications. And so now the word and the floor is to Matteo. Please, Matteo, you can start.
Hello, I'm Matteo, and I will speak about how to combine MCA and CBA in order to have a combined approach for improve the smart grid analysis. As previously introduced, the CBA and MCA are tools for supporting decision making, and those tools are different because they are based on different philosophies. As can you see, CBA has the main positive aspect the fact that it is rigorous and rational, and it is characterized by a formalized procedure, and also it is widely acknowledged since it is has been used many decades ago, and but has main negative aspects. CBA seems not so suitable for large projects, because it is difficult and expensive to be exploited, and it requires a lot of data, and it is impossible to assess soft effects. On the other side, MCA is characterized by a very flexible approach, and it does not require monetization of impact. So it is possible to assess soft effects, and thanks to the weight of criteria can ensure the participation of stakeholders. But this tool can introduce an excess of subjectivity, and if it is not well formalized, the risk of double counting is high. And as the professor said before, it's lacking respect in the carbon criterion, so the profitability of the best option is not ensured. But these two approaches are not mutually exclusive, but they are complementary tools, since they can be combined in order to have a monetary evaluation of tangible impact with a cost-benefit analysis, and non-monetary evaluation of not monetary impact with the MCA. In this way, with this combined approach, it's possible to relieve the respective loss by emphasizing the respective strength of those methods. In particular, in literature, these combined approaches have been analyzed, and there are two main families. The first family The first family say that the CBA can be considered as economic criterion of a MCA framework, where CBA is strictly focused on tangible impact, while MCA focuses on intangible impact. On the right is depicted another approach that combines MCA and CBA, that say that MCA can be used for select a subset of interesting investment options, while CBA can be used then for evaluate the economic viability of the selected option. Now I will present MCA-CBA approach for smart grid assessment that has been developed within the Annex 3 activities. And this combined approach completes with the international guidelines on project assessment as the guidelines divided by JRC that try to extend the CBA analysis of EPRI by including some technical impact on smart grid. And the approach that we present formalizes those guidelines, introducing the evaluation on three different areas: the economic assessment, the smart grid deployment merit assessment, and the externality impact assessment. By combining these three evaluations, we can obtain an overall evaluation of each project on smart grid. And in more detail, the decision-making problem of identifying the best option is decomposed by a hierarchy of criteria in which the three branches are independent, and these branches are similar since they have more than one layer, and each layer is defined according to the principle of abstraction. And the first branch is focused on the evaluation of monetary impact, and the lower level of the branch is characterized by the terminal criteria. In this case, the terminal criteria are the economic performance indicators that are produced by a CBA. So the net present value, the internal rate of return, and the cost-benefit ratio. So this framework requires a cost-benefit analysis of the alternatives under analysis, and this CBA can be made according to international guidelines such as EPRI or JRC. And obtain a positive CBA evaluation may represent a requirement for defining a limited subset of projects to be further analyzed by the MCA framework. The second branch is assess the contribution toward the smart grid realization given by each project option. This branch is defined on the basis of the JRC guidelines, in which are defined several policy criteria that represent some general benefits for the energy sector defined by the European Commission. And each policy criteria is related to several key performance indicators that are the terminal criteria of the branch. And it's worth noting that this evaluation is output-based, since only the produced effects of the project option are evaluated instead of the technical feature of the infrastructure. And this is something that is derived from JRC guidelines. And in this slide, you can see the 6 policy criteria and and the related key performance indicators, for example, the security and quality of supply can be evaluated by considering 5 KPI and, for example, the voltage quality performance. The third branch assesses the externalities produced by the project option, and it is organized in 2 layers. In the upper layer, we have thematic areas that are useful for group different single impacts, and the sum of the alternatives on are measured by qualitative and quantitative index that are related to each single impact. It is assumed that the second level criteria are mutually dependent, so each single impact can influence more than one thematic area. Now I will introduce a case study where we use the MCA-CBA framework for analyze some distribution green planning alternatives. So we study a set of active distribution network planning options that has been divided for using a multi-objective algorithm, and each of these planning options consists in traditional network reinforcement and in fitting and sizing of distribution energy storage as non-network solution. Each alternative has a time horizon of 10 years, and the topology of the network is considered as fixed, and for each bus we considered a load growth rate of 3%. And operation has been evaluated by a probabilistic load flow. The hierarchy of criteria previously introduced is general. Then we had to particularize it for fit with the decision-making problem at hand. So in this case, we choose to have just one economic criteria, that is the net present value, that has been considered by a particular CBA that encompasses only network reinforcement cost for line and substation upgrading, the cost of reactive power exchange with the transition system operator, and the cost of distribution energy storage device. So this is the investment by batteries and for operating. And the second branch also has been modified. We found 3 policy criteria with the 6 related KPI. So the first policy criteria is related to network connectivity and access to all categories of network users, and it is measured by the KPI 1, operational flexibility provided for dynamic balancing of electricity in the network. The second policy criterion has been evaluated by means of 4 KPIs, and so the security and quality of supply has been evaluated by combining the performances of the alternative on stability of the electricity system, with the duration of interaction and the frequencies of interaction per customer, and the voltage quality in terms of voltage variation. The third policy criterion concerns the efficiency and service quality in electricity supply and grid operation, and the KPI is the level of losses in distribution network, in this case. And so this is the final hierarchy, and we assign an equal weight for the 2 branches. So the economic evaluation has the same relevance of smart grid paradigm. And we evaluate the weight of each terminal criterion according to the hierarchical composition principle by giving the same relevance on criteria that belong to the same level. We have in this slide the performance matrix, so each KPI is a key performance indicator. So on the right, you can see the formulas that we use for evaluate each value that you can find in this matrix. We have 5 alternatives. The alternative 1 is the baseline scenario, and the alternative 5 is the alternative that has the higher net present value. And you can see in the second part of this matrix is related to key performance indicators. You can find in this slide the formula, so I will be fast here. Okay, and this is the result of the evaluation. We use a methodology that combines the principle of analytical hierarchy process, and by automatizing it, and we obtain this result where the alternative A5 is the best one because it achieves the higher overall score when both branches has the same relevance. And we in this second table, you can see that the partial scores, you can see that the A5 has the higher economic score, while it's the alternative A4 that has the higher smart grid merit score. And by means of a sensitive analysis on criteria weight, we saw that when the relevance of the economic branch is less than 0.24, the best alternative is the alternative A4, while otherwise the best alternative is the alternative A5. This shows how it is important that government body decide which are the relevant issues of its type. Okay, and here this is a brief description of 3 real cases of cost-benefit analysis and multicriteria analysis combined. For example, these 2 methods combined have been used by the Italian regulator for understand when remunerate DSOs for operating storage for network issues. Multicriteria analysis has been used for evaluate smart grid demonstration projects in China and Singapore, and also within the Annex 3 we developed an investigation about the Italian smart metering infrastructure. Okay. Now I will conclude that smart grid generates wide range impact which outclass the power system borders. So a new assessment approach for properly considering the potential of smart grid technology and their effect on society is required. A joint MCA-CBA approach cannot clasp the weaknesses of both methods and can emphasize the respective strengths. MCA and CBA framework allows decision makers to assess impact on different areas, assess monetary and intangible impact together, reduce data requirements for the assessment, and promote an active participation of stakeholders. So develop automated CBA MCA tools allows to analyze easily and track large sets of planning options. And the future work on this topic are a lot because we are just the beginning, and for promoting smart grid we need a simple and shared framework for project assessment in order to encourage the comparison of projects among different regions in the world. And we need data sharing about smart grid initiatives, and we need to improve the technical coverage of the use of this assessment framework. We need to better consider uncertainties and to develop common feasible scenarios. And finally, we need to find the best, an effective strategy for reduced subjectivity in the analysis and reduce in this way the personal biases that can be introduced in the weight elicitation process. And this is the readings, the bibliography that you can, if you are interested in a deeper knowledge.